This video is about the transformation of functions. Transformations of functions, if you understand all the different ways that a function can be transformed, meaning translated, so those are like basically shifts either up or down, that could be stretched or compressed, so like a dilation, or potentially even rotation. If you understand all of these things, it is such an incredible, like, it's like a superpower where you can look at a function that's written down and just kind of know what it's going to look like without even having to actually graph it. You can just kind of imagine what it's going to be like because you have this base knowledge of what a normal function looks like, something called a parent function. And then you can apply these transformations in your head and be like, okay, this is going to be like this. Let's let me talk about what that means. So if we consider a function like this, y equals x squared, actually, let's just do this. F of x is equal to x squared. This is a parabola. It's like the most basic possible parabola. We call this a parent function or a base function quadratic. Quadratic being a polynomial of degree 2. The graph itself looks like a parabola, and the vertex of the graph, a minimum in this case, is at 0, 0. Think about all the different things that I can do to modify this function. For example, what if I said I'm going to take a value away from x? Take 1 away from x in the square. So what I've done here is I've just subtracted 1 from x before squaring it, right? So before really applying the function or the squared part of the function, I'm just subtracting 1 away. Notice how, so the blue line is my transformation, is how the function was transformed, and it moved 1 to the right. Now this might seem counterintuitive, like I subtracted 1, not like negative means go to the left, right? Well, think about this, okay? You can plug numbers in here and prove to yourself that this is indeed a shift of 1 to the right, and that kind of everything inside here, everything that you do inside of the parentheses sort of here is going to manifest opposite the way you might think it will. But think about this. If you are in the United States of America, you're probably familiar with something called daylight savings time. Daylight saving time is when we add or subtract an hour essentially from the day. And I don't know, it started back in like after World War II or something, or after the Great Depression, and we had to like something about farmers. I don't know. Basically, now everybody thinks it's stupid. And think about what happens when we do daylight saving time. We roll the clocks. We push the clocks forward an hour, right? So if it's like 7 p.m. or like it happens at midnight, but like where it would have been 7 p.m. now it's 8 p.m. So you kind of like, it's like saying x plus 1, right? You're adding that hour of time. But what does that actually do to like your day? Like what does that do to your schedule for the next day? You're going to have to wake up an hour earlier. You're losing an hour, right? And then the opposite of that, when we revert from daylight saving time or whatever it is, I might have this backwards, but then you roll the clocks back. So like where it would be 4 p.m. now it's 3 p.m. That's great because you just gained an extra hour of like sleep, right? So when you subtract away from your hour, you're actually getting more time back. That's kind of the same idea of why it is that a x minus 1 produces a shift of 1 to the right. Anyway, that was a long-winded explanation of how this works. If I did a plus 1 here, we shift left to right. So a horizontal translation happens when we add or subtract from our original input of x. Now, so let's pretend I didn't do anything to that x. If I added 1 outside of this, so if I add 1 to the outside after I did my squared thing, that results in a shift of 1 up. And this should make complete sense. Your y values, so x values are x values, you're then adding 1 to the output of the function, so you're making everything shift the 1 up. If you subtract 1, you're moving things down, right? And the other things that you can do, or for example, multiplying everything by -1, you're going to make everything invert. Okay, so there's 2 different ways you can. What if I multiplied the -1 on the outside? It's this vertical shift. But if I had a -1 on the inside, does anything happen? At first, you might think not. But if I had something else on the inside and I multiply that x by -1, well, now, yes, it actually does sort of like a horizontal flip, and that's because I'm applying that -1 thing right to the input itself. let's look at this all another way. And those are all the different, well, it's not all the different ones. We could also have some vertical stretches and compressions, but I want to show you this and show this to you in a little bit different way. I have defined f of x as x squared, okay? If I then take f of x, like of course it's going to graph the exact same function f of x. If I subtract 1 from x, what do you think will happen? You shouldn't say that this is going to move the graph 1 to the right. It's a horizontal translation 1 to the right. This is the exact same thing as saying x minus 1 quantity squared. If I add 3, it's going to move 3 to the left because this is the exact same thing as saying x plus 3 quantity squared. If I, again, like let's say I subtract 7, that's going to move the graph down 7. It's going to move my like a reference point of 0, 0 down 7 units because we're taking our y value, f of x is a y value, and subtracting 7 from it. So we're going down 7. Okay, what if I multiplied all of this by not -1, but let's say like 2? Okay, what's this? Is this affecting the y values or the x values of a graph? Well, it's kind of hard to see here because I haven't done anything in the horizontal direction at all. So what if I took that 2 away, okay, and I said, all right, now I'm looking at this, and I notice there's a 2 right here. So if I multiply, this is an x value of 2. If I put a 2 out here and that vertex changed locations, I'd be making a horizontal change. So by putting a 2 out in front, am I giving a horizontal or vertical change? So I type the 2 in and it just gets skinnier. So this is actually just a vertical change. So when you multiply, again, this highlighted part is the output. We're multiplying the output, which having a vertical change. And when you multiply by an output, a number here that's greater than 1 or greater than -1, that's going to create what's called a vertical stretch. So you can imagine if you grab the bottom of this parabola and you grab like the top ends and you pulled up, it's going to be like it's going to stretch up like a piece of gum. Like let's say you take a piece of gum and it's wet and disgusting and you grab either end of it, you pull it, yes, it gets taller, but also shrinks. It also results in like a horizontal kind of shrink. Now there's also strictly a horizontal compression. If I multiply this 2 by x, notice how the x value is going to change here. If I multiplied x by 2, notice how now it actually is only over 1. But also notice how it was a compression now, like we actually reduced the x kind of values, whereas when we multiplied the outputs by 2, we increased the y values. So it does this kind of backwards from what we expect type of thing. The reason for this is what we really did was we only subtracting 1 away from x, which is why it only shifted 1, and then everything that was shifted by 2. Like that's the same thing as 2x minus 2, but that's a little bit advanced, and that's totally okay. The point is, if we multiply the x directly by something, it results in a horizontal change, and that horizontal change is either going to be a compression or a stretch, depending on if my value is greater than 1, it's a compression, and if it was less than 1, like let me show you, if I put 1/2, well, now it's a fat boy now. We call it a fat boy in math. That's actually the correct term. And results in this horizontal stretch. So let's put this all into play here and let's look at another f of x thing. If I take this purple parabola here, which is the exact same thing as x squared, and I wanted to move it 5 to the right, 2 down, and then shift everything and then like put some compressions on it. Let's see what that means. I want to move 5 to the right, so I'm going to have to do -5. I want to move it down 2, so I'm going to put -2. So now I've successfully moved my graph down 5. Right to the right 5 and down 2. And let's say I wanted to apply a vertical stretch by like a factor of 2, or as 2 is too normal. Let's apply a vertical compression. So let's make it like a fat boy, more of a fat boy, or like reducing its height kind of. It's going to compress down, but I still have moved it over 5 to the right and down 2. Like, right? See, that 1/2 isn't being multiplied by that 2, right? So the vertical value didn't change. The horizontal value didn't change, but it's increased, not of the original point, but all the other y values did change. Like, whereas, I had a y-intercept here. If I had a y-intercept Here, really, that y-intercept now is like this one came down and was there, or that one right there came down to be right there. So that's what's happening here. We only really have these many things. If I multiply this by a -1, it just is going to flip upside down. So these are the transformations that can happen to a function. And what's cool is that it doesn't matter what this original function was, right? If I had x cubed, all of those same transformations still apply the same way. And the best part of all of this is that if a function is written in a in a particular kind of way, and the kind of way for a quadratic, which is the most common one you're probably going to see, it, with the exception of trigonometric functions, is going to look something like, it's going to be in this form right here. I'm just going to type this in and it's not going to work out. But if I type in a times x minus h quantity squared plus k, I want to look at these values. Okay, a applies, it has to do with a vertical stretch or compression, right? We saw that when I multiplied by 1/2, it resulted in a vertical compression. If I had multiplied this by 5, it would have been sorry, I just got rid of the -2. It's a vertical stretch. Okay, that's what's happening there. This h has to do with the horizontal shift. Let me put this back as a squared so you can kind of see how this works. Oh, I'm going to have to make this like different. Oh, I didn't want it to be 2. I want it to be squared. That's what happened. Sorry. Okay. So we had when we had the a, that was a vertical stretch. Now when we subtracted a value from h, we subtracted a value from x from the input. It resulted in a shift, right, of to the right when we subtracted, or if it was positive, it'd be a shift to the left. So for example, for let's see, for the purple one, right, we shifted 5 over, so that point of that vertex shifted 5 over. So really, this h value is the coordinate of the vertex. Because if I started at 0 and I just subtracted like 6, then I would be 6 to the right. That would be the x coordinate of the vertex. If I added 6, I'd be 6 to the left. So -6 would be the x coordinate of the vertex. And similarly, k is going to be the y value of the vertex. So in this on the purple parabola, when I subtracted 2, I just brought the vertex value down to 2. So it makes sense then that h comma k is the vertex of a parabola if you are looking at this kind of equation, which is known as the vertex form of a quadratic. And if you are given this kind of form, you can easily see what all the transformations were. Okay, I did this. I shifted left or right based on h. I shifted up or down based on k. And then I did a vertical stretch or compression based on what a is. And something you'll notice also is that this value of a is present for every polynomial. Let me give you an example. Y equals ax plus b. You might be thinking, well, isn't it y equals mx plus b? Yes, it is. But when we talk about a line, that value of a has extra meaning as it's the slope, but still it has to do with the vertical like stretch or compression. Think about y equals x, right? If I put 5x, it makes it like it stretched everything out vertically. If I put 1/5 x, it's going to kind of push everything down and compress it vertically. So this a value is still there, right? And it's there, and you've seen stuff like, 60x cubed minus 5x squared plus 3x minus 2. And this might seem like something very difficult to deal with, but there's your a value. It's still there. So a values will always be there for polynomials. Anyway, this has been a video about the transformations of functions. And the reason it's important to know these things is because you will come across stuff, like this, y equals 3 times x minus 2 quantity squared plus 5. And you'll have to know just based on this, like, what's the vertex of this parabola? And if you know that this is the base function is a quadratic, is a parabola, it's just x squared. Well, I know that it's going to be skinny because of this 3. It's greater than 1. I know that the vertex is going to be at 2, 5, which it is here. And then basically, I know almost everything about it. I know that it won't have any real solutions because it's not crossing the x-axis. These are all important things that you can kind of discern just by looking at something. And it's so clutch. It'll come in so handy if you can get comfortable with transformations as you move through your math career.